If you hand your teenager a circuit board and a sensor, will they learn more by wiring it up and watching an LED blink, or by writing Python code to analyze the data it collects? That question sits at the heart of every parent's Arduino versus Raspberry Pi decision, and the answer shapes which technical skills your kid actually builds. I'm Dr. Priya Mehta, a child developmental psychologist who specializes in how kids learn computational thinking through hands-on tools, and I've watched hundreds of teens succeed and struggle with both platforms. You're listening to the STEM Lab podcast. Quick heads up before we dive in. Everything you're about to hear, the research, the data, the script, all of it is written and verified by real human authors. But the voice reading it to you, that's AI generated. Just wanted to be upfront about that. Now, if you've been listening to this show for a while, thank you. Seriously. I know you've got a million podcast options, and I'm glad you keep coming back to this one. And if you're brand new here, welcome. We drop new episodes every Monday, Wednesday, and Friday covering hands-on learning, robotics, renewable energy, citizen science, all the ways kids build real technical skills. Let's jump right in.
For most teenagers, Arduino delivers faster, more tangible wins in physical computing and electronics fundamentals, while Raspberry Pi excels at software-intensive projects and computational thinking. The Arduino versus Raspberry Pi debate for teens isn't really about which platform is better overall. It's about matching your teenager's current interests and learning trajectory to the right tool. This comparison breaks down technical requirements, skill outcomes, and progressive learning paths so you can choose the platform that builds industry-relevant capabilities your teen can actually use. I'll walk you through compatibility requirements, hands-on versus screen-based learning trade-offs, and how each platform prepares your teenager for different career pathways in science, technology, engineering, and math. You'll leave knowing exactly which investment fits your home lab setup and your teen's developmental readiness. Let me start with a quick comparison of what these platforms actually do differently. Arduino focuses primarily on electronics, sensors, physical computing, and embedded systems. Raspberry Pi focuses on software development, general computing, Python programming, and projects involving artificial intelligence and machine learning. When it comes to screen time, Arduino keeps it minimal. Your teen mostly manipulates hardware and uploads brief bits of code. Raspberry Pi involves significant screen time because it runs a full desktop environment with extended coding sessions. The technical barrier is lower with Arduino. It's fairly plug-and-play with sensors, and you get immediate physical feedback. Raspberry Pi has a higher barrier. Linux familiarity helps, and troubleshooting operating system issues is pretty common. For skill outcomes with 15 to 17-year-olds, Arduino teaches circuit design, sensor integration, the fundamentals of C++, and real-time control systems. Raspberry Pi builds fluency in Python, web development, database management, and computer vision basics. Industry preparation differs too. Arduino prepares teens for embedded systems engineering, Internet of Things device programming, and robotics firmware. Raspberry Pi prepares them for software engineering, data science, full-stack development, and machine learning. Cost-wise, an Arduino starter kit runs about $50 to $80, and you can expand it with individual sensors that cost $5 to $30 each. A Raspberry Pi board costs around $55 to $100, but it requires a monitor, keyboard, and mouse unless you're using a headless setup. Now, let's talk about screen time versus hands-on learning balance. When you're weighing Arduino against Raspberry Pi for teens, the screen time differential matters more than most comparison articles acknowledge. Arduino keeps your teenager's hands on physical components for 70 to 80% of project time. They're wiring breadboards, soldering headers, calibrating sensors, and watching LEDs respond to their code. The actual programming happens in short bursts. Write a function, upload it to the board, test the physical output, iterate. Your teen might spend 20 minutes coding, then an hour building the circuit and fine-tuning sensor placement.
That tactile loop reinforces cause and effect learning in ways pure software can't match. Raspberry Pi flips that ratio. Your teenager sits at a screen running a full Linux desktop environment, debugging Python scripts, managing file systems, and troubleshooting software dependencies. It's closer to professional software development, which absolutely has value, but it eliminates the immediate physical feedback that helps concrete thinkers grasp abstract programming concepts. If your teen already struggles with sustained screen focus or gets frustrated when code doesn't produce visible results quickly, Arduino's tangible outputs offer guilt-free learning momentum. Here's what the lab specs look like for Arduino. The Arduino Uno Rev 3 runs on 5 volts via USB or 7 to 12 volt DC adapter. Check the show notes for a link to the current price. There's no operating system to maintain, no display required. Code uploads in seconds from the Arduino IDE, which is free and compatible with Windows, macOS, and Linux. It's offline capable. You can write and test code without internet once the IDE is installed. Durability is excellent for repeated student use. Accidentally reversing polarity might blow the voltage regulator, which is replaceable for around $2, but the microcontroller itself tolerates beginner mistakes pretty well. For Raspberry Pi, the Raspberry Pi 5 with 8 GB of RAM requires a 5-volt, 5-amp USB-C power supply. Check the show notes for a link to the current price. The official adapter is strongly recommended because cheap third-party supplies cause intermittent crashes. You'll need a micro SD card, minimum 32 GB class 10, plus a monitor, HDMI cable, USB keyboard, and mouse for initial setup. It runs Raspberry Pi OS, which is based on Debian Linux and free. It's internet-dependent for package installations and updates. Cloud integration is optional for advanced projects like IoT dashboards and remote access, but core functionality works offline. There's a durability concern, though. SD card corruption from improper shutdowns is common with teen users who forget the shutdown procedure, so budget for backup cards.
Moving on to programming language pathways and career readiness, Arduino uses a simplified version of C++, compiled and uploaded to the microcontroller's limited memory. The Uno has 32 kilobytes. This constraint teaches resource-efficient coding. Your teen can't bloat their program with unused libraries or sloppy loops because the board literally won't accept it. They learn to write tight, purposeful code that does one thing well. That's exactly how embedded systems engineers work in automotive, medical device, and aerospace industries, where memory is precious and reliability is non-negotiable. The Arduino IDE supports drag-and-drop block coding for beginners through Arduino Lab for MicroPython and Scratch extensions, but serious projects require text-based C++. Within about 10 to 15 hours of platform use, your teenager will encounter pointers, data types, and memory management. These are foundational computer science concepts that transfer directly to university-level coursework. Raspberry Pi runs Python natively, which is the industry standard for data science, machine learning, web backends, and scientific computing. Your teen writes and executes code in a familiar desktop environment using Thonny, which is beginner-friendly, or Idle, or VS Code. They access the full Python ecosystem: NumPy for data analysis, OpenCV for computer vision, Flask for web servers, TensorFlow Lite for on-device artificial intelligence. This is professional-grade tooling. It's the same libraries data scientists use at Google, research labs, and biotech companies. If your teenager wants to explore teaching kids AI and machine learning, Raspberry Pi's computational horsepower makes it feasible. Arduino can't train neural networks or process video streams. It excels at controlling things in the physical world, not analyzing large datasets. Neither platform requires subscriptions for core functionality. Arduino IDE is open source and free forever. Raspberry Pi OS and all standard Python libraries are free. Consumable costs are minimal. You'll replace breadboard jumper wires, about $8 for 200 pieces, and LEDs, around 10 cents each, as they inevitably get lost or damaged. Both platforms integrate into progressive learning paths that scale from beginner tutorials to competition-level builds. Let's look at hardware expandability and real-world applications. When comparing Arduino versus Raspberry Pi for teens through the lens of expandability, Arduino wins for sensor ecosystem breadth and plug-and-play compatibility. Grove systems, Adafruit breakout boards, and SparkFun sensors use standardized connectors. Your teen plugs in a soil moisture sensor, temperature and humidity module, or ultrasonic distance sensor without soldering. Upload example code, see readings in the serial monitor, done.
This makes Arduino perfect for renewable energy science fair projects that need solar panel voltage monitoring, wind speed sensing, or battery charge tracking. The real-time control capabilities let your teen build a maximum power point tracker or automated sun-following mount. These are projects that teach electrical engineering principles through hands-on iteration. Raspberry Pi's GPIO pins can interface with sensors too, but the 3.3-volt logic level creates compatibility headaches. Most Arduino sensors run 5 volts, and there's no built-in analog input. Your teenager needs to add an ADC chip, an analog-to-digital converter for basic temperature or light sensing. That introduces circuit complexity that distracts from the core project. Where Raspberry Pi shines is computational projects that need processing power, analyzing environmental data from citizen science monitoring kits, hosting a local web dashboard for water quality testing results, or running computer vision algorithms to identify invasive plant species in field photos. Arduino expandability follows a modular shield system. LCD displays, motor drivers, GPS modules, and Ethernet adapters stack directly onto the main board. Your teen builds a weather station that logs data to SD card, or a line-following robot for advanced robotics competitions, by adding one shield at a time. Each edition teaches a new subsystem, serial communication protocols like I2C and SPI, interrupt handling, multitasking basics. Raspberry Pi expandability is software-driven. Your teenager connects USB peripherals like webcams, microphones, game controllers, installs packages with a terminal command, and suddenly has access to capabilities Arduino can't touch. Running multiple programs simultaneously, streaming video over network, storing gigabytes of sensor data. For challenges that require data collection and analysis, Raspberry Pi eliminates the separate computer step entirely. Here's a compatibility note. Arduino works seamlessly with most robotics kits designed for progressive skill building. Raspberry Pi requires kits explicitly designed for its GPIO pinout and Linux operating system. Check compatibility before purchasing. Now let's talk about cost architecture and long-term investment value. The upfront cost difference between Arduino and Raspberry Pi for teens is negligible. Both starter kits hover around $60 to $100. The long-term cost trajectory diverges based on project scope and failure modes.
Arduino's per-project cost is predictable and granular. Your teen wants to build a temperature-controlled fan? Add a DHT22 sensor for about $5, a relay module for about $4, and a 12-volt fan for about $8. Total incremental cost? Roughly $17. Project fails or gets abandoned? You've lost $17, and the sensors can be reused in the next build. Replacement boards cost around $25 for genuine Arduino Uno or $8 to $12 for functionally identical clones. This low-stakes environment encourages experimental learning. Your teenager isn't afraid to try something risky because failure doesn't mean replacing a $100 computer. Raspberry Pi projects often require larger, less reusable investments. Building a smart mirror? You need a two-way mirror panel for $40 to $80, dedicated monitor for $80 to $120, custom frame materials. The Raspberry Pi is a small part of total project cost, but failed projects leave you with single-purpose components that don't transfer to other builds. The board itself is more fragile. SD card corruption from power loss during writes can brick the system until you reflash the card, and GPIO pin damage from accidental 5-volt input, which is an easy mistake for beginners, can destroy the board entirely. Here's the value proposition. Arduino teaches debugging through iteration at low financial stakes. Raspberry Pi teaches system administration and software architecture, but requires greater supervisory support to prevent costly mistakes. For middle school students new to electronics, Arduino's forgiving cost structure supports independent exploration better. Neither platform locks you into consumable subscriptions, but online tutorials and project libraries differ substantially. Arduino benefits from 15+ years of community documentation. Nearly every beginner mistake has a forum post explaining the fix. Raspberry Pi's rapid hardware evolution, the Pi 3, 4, 5, and 0 variants, means tutorials written for older models often require adaptation. Your teen will spend more time troubleshooting operating system level issues, like why won't this Python library install, with Raspberry Pi compared to Arduino's simpler software stack. So who should choose Arduino? Choose Arduino if your teenager prefers working with their hands and gets frustrated by long software debugging sessions. If they want to build robotics projects, sensor networks, or electronics that interact with the physical world. If they plan to pursue mechanical engineering, electrical engineering, or embedded systems careers, if they need screen time limits but should still develop coding skills, or if they struggle with abstract concepts but thrive when code produces immediate visible results. LEDs light up, motors spin, servos move.
Arduino fits naturally into progressive learning paths that start with screen-free coding and advance to microcontroller programming. If your teen has already mastered basic circuits and wants to add programmability, Arduino is the logical next step. It's the platform I recommend when parents ask, how do I keep my teenager engaged in science and tech without adding another screen-based activity to their day? The tactile feedback loop keeps hands busy and minds focused without the dopamine drain of scrolling or gaming. Who should choose Raspberry Pi? Choose Raspberry Pi if your teenager already has strong computer comfort and wants to learn Linux, Python, or web development. If they plan data science, software engineering, AI research, or computational biology career paths. If they need a platform for media projects, home automation, or networked applications. If they benefit from having a dedicated learning computer separate from family devices, which lets them experiment with system settings without consequences. Or if they want to work on citizen science projects requiring data analysis or machine learning. Raspberry Pi is better for self-directed learners who can tolerate troubleshooting operating system issues and reading documentation to solve problems independently. It's a full computer, which means your teenager gets stuck on the same problems professional developers face: library version conflicts, permission errors, network configuration bugs. That's valuable learning, but it requires patience and stronger reading comprehension than Arduino's simpler arrow messages. For teens planning to study computer science in college, that early exposure to Linux environments pays dividends when freshman coursework assumes basic terminal fluency. If you're building a dedicated home lab, Raspberry Pi can serve double duty as both the learning platform and the lab computer, running CAD software for 3D printing projects, hosting project documentation, controlling environmental sensors. Arduino requires a separate computer for programming, but takes up negligible desk space once deployed.
Let me answer some frequently asked questions. Can a 13-year-old learn Arduino or Raspberry Pi without prior coding experience? Yes, both platforms support absolute beginners, but Arduino's learning curve is gentler for teens without coding background. Block-based programming environments like Arduino Lab for MicroPython let your 13-year-old drag visual code blocks that immediately control physical components, flash an LED, read a temperature sensor without syntax errors derailing progress. Raspberry Pi requires more foundational computer literacy, file systems, operating system concepts, keyboard shortcuts, before your team can write their first working program. That can frustrate concrete thinkers who want to see results quickly. If your teenager has zero coding exposure, start with Arduino and transition to Raspberry Pi after they've built 5 to 10 successful projects that demystify how code translates to action. Do I need to buy a new Arduino or Raspberry Pi when my teen outgrows beginner projects? No, both platforms scale from beginner to professional-grade work without hardware replacement. Arduino Uno remains relevant for advanced projects. Professional engineers use it for industrial prototypes and production systems. Your teenager simply adds more sophisticated shields and sensors as their skills progress, or upgrades to specialized boards, Arduino Nano for compact builds, Arduino Mega for projects needing more input and output pins, while keeping all their existing knowledge and component libraries. Raspberry Pi similarly grows with your teen's capabilities. The same Pi 5 that runs beginner Python tutorials today can host machine learning models, web servers, or robotics control systems. The limiting factor is your teenager's skill and imagination, not the hardware capabilities. Which platform is better for science fair projects, Arduino or Raspberry Pi? Arduino is generally better for hands-on science fair projects, requiring sensor data collection, physical control systems, or real-time responsiveness, while Raspberry Pi excels at projects involving data analysis, machine learning, or computational modeling. If your teenager is building a renewable energy efficiency comparison using solar panel kits, Arduino's analog inputs and low power consumption make it ideal for continuous monitoring over weeks. If they're analyzing months of environmental data to identify pollution patterns or training a model to classify plant diseases from photos, Raspberry Pi's processing power and Python libraries handle those computational tasks that would overwhelm Arduino's limited memory. Many advanced fair projects actually use both. Arduino collects sensor data, Raspberry Pi processes it and visualizes it, teaching your teen how professional distributed systems integrate specialized components.
Here's the bottom line. The Arduino versus Raspberry Pi decision for teens isn't about picking a winner. It's about matching your teenager's current developmental zone and career interests to the right learning tool. Arduino builds electronics intuition and embedded systems thinking through immediate physical feedback with minimal screen dependence. Raspberry Pi develops software architecture skills and computational reasoning using professional-grade tools and unlimited processing headroom. Most teens eventually benefit from learning both platforms, but starting with the right one prevents frustration and builds confidence through early wins. Watch how your teenager approaches problems. If they'd rather take something apart to see how it works, start with Arduino. If they prefer reading documentation and logical troubleshooting, Raspberry Pi fits better. Both pathways lead to legitimate industry skills. Embedded systems engineers and software developers both earn excellent livings solving fascinating problems. You're not limiting your teen's future by choosing one platform today. You're giving them a solid foundation to build genuine technical capability one project at a time.
Thanks for sticking with me through this episode of the STEM Lab podcast. New episodes come out every Monday, Wednesday, and Friday, so you'll have fresh content waiting for you 3 times a week. If this episode helped you think through which platform makes sense for your teenager, I'd be really grateful if you left a 5-star rating and a quick review. That's honestly how other parents find the show, and it makes a huge difference. And hit subscribe or follow so you get notified the second a new episode drops. I'll see you next time.